Okay, thank you. So in the structure of the operating system, like if it is providing a services or this operating system provides service to the task, then these services are also referred from the three key element perspectives. Like number one is what are the abstraction layer of operating system that gets provided to an application. That is what we call to be as in process management, thread management, file management, or the different APIs that is a socket that we are supposed to get it interconnect with each others, and the memory management. And if you look at the mechanisms, then the way in which these abstraction layers are going to be provided, okay, the abstraction layer services are going to be provided is again based on the mechanism which makes use of this particular processes. Like for example, create. These are the functions. This create, schedule, open, write, allocate. So these are the mechanism by virtue of which this abstraction layer processes would be provided. And these mechanisms would be built on some sample policies. Like, for example, if I want to schedule the task or create the task, then which task is expected to be scheduled, that is determined by the underlying scheduler as a software that is being written. So this least recently used task can be used as a scheduling policy or scheduling policy as for the scheduler, or earliest deadline first is the task basis that can be used for this particular mechanism. I mean, the key element that happens to be there is an abstraction layers for user application, mechanism, that is the different functions or operations that creates that particular abstraction layer services, and then the policies which builds up this particular mechanism. So this is a three-tier system that happens to be there in the structure of this operating system. Fine. So let's see, there happens to be two basic principles of design of operating system. So it happens to be separation of mechanism and policy. So this part, separation of mechanism and policy by implementing flexible mechanism to support the policies. Okay, this is one of the approach, the two operating system design principles happens to be this. And again, as I am telling you that this particular design principles or this operating system design is oriented towards what is expected. What is expected for an application, what is expected as a category of applications. That is what it is written, that we could able to separate out the mechanism and policy by implementing the flexible mechanism to support this particular policies. Means the way in which this create is to be used could be definitely different. The task creation, for example, could be different in order to leverage the different policies which would be underlying to this particular mechanism. Or for example, scheduling, it can be written on to making these policies to be as a flexible one. So it's again, as I'm saying, it's a design principles. So these are again based on the targeted application category of an applications. Then optimize for common use, for example, where will the OS be used? That is what the the important design principle that is to be understood. And what will the user want to execute on that machine? What kind of application that user want to execute onto that machine? That's what I said. And that is what I have given an example which is very relevant to the current time. That if I want to run the server that is used to manage the devices which are being connected on Internet of Things, which are being connected on IoTs, which are being connected on clouds. And if I want to manage and make use of those resources very optimally, then I might not make use of the OS which is being currently used for my desktop or laptop operating system or these particular machines. I might need different services of operating system to be used for this. I mean, these kind of approaches are definitely going to be there. These kind of design principles are definitely going to be there. That is what will be the user want to execute on that machine is again very important question in order for the design principles, as well as what are the workload requirements. Right? A workload requirement happens to be there, whether it is going to be for meeting up the timeline, meeting up the execution time, or more number of tasks to be executed per unit time, throughput or execution speed, throughput or execution profiles. So I mean, again, these are going to be the different workload requirement, and according to that, the design principles are getting governed in order to design an operating systems. Okay, and these particular design principles are basically defines one operating system structure from other operating system structure. That is what, as a baseline discussion in the structure of operating system, we need to understand these two criteria based on which the operating system designs are always being there into the picture. Getting it? So that was the reason why we are discussing this operating system design principles at the moment. Fine. So let's move ahead and try and understand that there happens to be different structures of operating system, which I'll be quickly reviewing of it, because I'm sure that these systems are known to you. So that is what I just intend to make this particular fast review of it, right? So general purpose OS is a very large program that we understand, like Windows OS is there, Linux OS is there. So these are going to be a very large program, as we know. The various ways to structure the operating system is like, for example, we can have the simple structure as we can see it from the MS-DOS kind of things, or we have some more complex than MS-DOS. We can see that it's an Unix structure OS, or we might have some kind of layered kind of things where the abstraction, the services are being brought at some different abstraction layers for facilitating to the user, and this is not different than what you can understand as a 7-layer OSI model for networking. Okay, so this very pardon me, since morning I'm in the meetings and discussions so heavily that it's really not being okay. So just have a minute break for water, then I'll continue. Okay, so as we were discussing that the services of OS would be brought into different categories of the layers, and as I was telling you, this is none different than what you are already understood as a 7-layer OSI model, where we have hardware, physical, session, right, Mac layer, application layer, all these layers are there. So that's what we say, that application service providing in the form of the abstractions. And then we have got the microkernel, which is more specifically to be a machine dependent kind of operating system. We mostly would understand for embedded systems, microkernel and Linux. These are the two OS that would be concerned to us. We will not be harping onto the layered and this simple MS-DOS kind of structures. Okay. So for sake of completion, I have mentioned here 4 structure, but to be very honest, we are very keen on understanding the more insights into this Unix-like, that is a Linux kind of operating system, and this microkernel operating system. Fine. So let's understand and review very quickly simple structure called MS-DOS. And I think this is what known to you by ages, right? Even in 11th, 12th also, you might undergone to this OS basics, MS-DOS OS basics. And in first year, definitely, I know you are undergone for it. So you can see that the interaction of this, like ROM bias device drivers are being there, which is basically called as an self bias, right? So it is called as an basic input output systems, or it is called as an POST also many times, power on self test kind of things. So if everything is being there for health monitoring operations, we have this kind of particular post and ROM bias device drivers, followed by the MS-DOS device drivers. And then we have got resident system programs, and then we have got application program. Concept of OS will never change irrespective of the any kind of structuring that it might undergo. Okay, that's what you can see, that from application program to an underlying hardware, all the things are being structured, organized in different layers, and that is what we call to be as a structure of operating system, nothing else. Okay, so in this particular MS-DOS, you can see that it is written to provide the most functionality in the least space. This is a feature of MS-DOS kind of things. It is not divided into modules. That means it is a monolithic kind of operating system. It is not heterogeneous operating system, or this is not going to be a microkernel kind of operating system. So this is going to be a monolithic operating system where there is tightly coupling of the services among each other. That's what we call to be as an provide most of the functionality in least space. It is not divided into modules, as we say. It's, although MS-DOS has same structure, its interfaces and levels of functionalities are not well separated. That's what I said. It's going to be a monolithic kind of operating system. Then if you see the Unix kind of things, which is simple, or sorry, which is non-simple kind of structure, you can see that there are so many things which are being there into it. Again, the concept should remain same. We have got different terminal controllers, device drivers, device controllers, memory controllers, physical memory interface and all, which is being there as an hardware. Then we have got different kernel services, same services like the signal to termination handling, character IO system, terminal drivers, file system, swapping blocks for IO, disk and tape drivers. I mean, all these services happens to be there as an kernel. Here also I have got kernel interface to an hardware and system call interface to the kernel, that is to the application layer. Again, in the application layer also, what I have are the shells. Shells and commands, compilers and interpreters or system libraries again sits into one of the structure, one of the layer of structure, and then it's a user. Means in nutshell, if you refer, then if user wants to access the underlying hardware for its services, then it might need to first of all make use of this particular shell or command, right? Which are maybe pre-compiled, or it might need to be compiled in order to get understood to this particular services which are being written into the kernel. Because kernel services are most of the time are half-blown executable services. That they are called to be as a .ko files. That's called the kernel object files. Okay, so these are not executable files completely. They are said to be as an half-blown executable files. There is a specific reason for that. In order to build up more configurability, customability, and being able to add the new services into the kernel during runtime also. Okay, please mark my words. During able to, or being an ability to add the new services even during runtime of an application. In order to provide this kind of services, definitely the kernel object files are definitely referred to as an .ko, which is called as half-blown executables. Okay, so we have got half-blown executables libraries, even files for this kernel, and we have got kernel interfaces as we already seen. Terminal the namings and this particular names which are being used for the different services and all are different. Otherwise, the purpose is the same one. Like if I want to have the secondary device to be used, secondary memory to be used like hard disk and all, I need the disk and tape controllers in the form of the device drivers, or some device controllers are there. It might need some DMA access. It might, I mean, in order to have the floppy disk and floppy disk are not there, but in order to have this particular hard disk driving and all that, hard disk management and all that, you might need some device driver controls or the device controllers especially for this. I mean, all this is what we discuss is in line with the basic theme of operating system that we have seen, right? So quickly read this lines. It is basically limited by hardware functionality. The original Unix operating system had limited structuring. Unix OS consists of two separate parts. Number one is system programs and second one is kernel, right? And as we know, it's a system programs and this is what kernel. The kernel consists of everything below the system call interface and above the physical layer. There is an interface as we have seen many times. It provides the file system, CPU scheduling, memory management, and other operating system functions, a large number of functions for one level. So this kernel has got many functions which are being bundled. And this can, in being a Unix, being the system, it can even be added from the application perspective also. That is what we are seeing in the next structure that we are seeing to as a module structure. But before that, let's understand layered approach. In the ages or in the literature that you can see that operating systems are being referred to be as structured as an onion shell. This is very famous term that is being used as structure of operating system is like onion shell. Why it is being said? Because of this. You can say that it has got the zeroth layer referred to as an hardware. Then it keep building the layer like layer 1, layer 2, layer 3, layer n. Layer n happens to be as an user interface. So this layer can be a device driver. This layer can be your kernel services. This layer can be an hardware services. So what is the difference between these two? Unix kind of things, which and this particular layered approach. The basic difference happens to be that the privilege levels that every layer would offer in order to access its services. Like for example, if at all user layer wants to access the service which is being written at this layer, for example, scheduler layer, then you can see that it cannot directly access it because there is one layer in between. Okay. So this 0th layer is the highest priority layer, where nth layer is supposed to be as an lowest priority layer. Okay. So this lowest priority layer cannot access the service unless and until the permission for the access of service is requested and granted permission is sought in order to make use of this particular services. This is the most interesting part that happens with the layered structure of operating system. Okay, and that is what operating system provides, a very good, very tight kind of protection against getting it corrupt, against getting it damaged from its successive upper layers. And being this nth layer as a user layer, outermost layer as a user layer, there is no fear of having a corruption or the crashing kind of activity in operating system because of user intervention into it, because that is not possible. Okay, because access itself will not be granted. Getting it? So this is one of the very significant advantage that you would have with a Windows kind of system. So this particular layered approach is being used in the Windows operating system. So this is divided into number of layers, that's called level, each built on top of the lower layers. The bottom layer is 0 and hardware, which is the highest layer, is in user level, as we have seen it. With modularity, layers are selected such that each uses functions or operations and services of only lower level layers. It cannot make use directly, and see, this cannot use the layer 1. It has to go through this only. And that is what it provides, very strong kind of security and very high level of protection is being. After layered structure of operating system, so let's investigate microkernel system structure. So as the name itself indicates, microkernel, a bare minimum set of functionality or bare minimum set of services are only expected to be sit into the kernel space. Else otherwise every service is to be there for the user space. So it divides, or it happens to be with a two space called kernel space and user space. So when we have only bare minimum services there into the kernel space, this approach benefits in different ways that we'll investigate it very shortly. But microkernel is an approach where we have only few essential bare minimum services there into the kernel of this OS. Else otherwise, whatever services those are expected to be built from an application perspective, those services would be there into the user space of this particular operating system. So let's try and understand this in more detail. So when we are saying that it's a user space and kernel space, it moves as much as from the kernel space into user space. That means the operating system, even services, are not expect every service like as a monolithic OS structure as we have seen. Every service is not expected to be there seated into the kernel, but that service is to be migrated to the user space. And user space and kernel space, there happens to be an interaction as on when required for the embedded applications. Most of the time, these embedded applications do carries fewer number of services. That's what having all kind of services into the kernel unnecessarily consumes a lot of memory. And we understand the embedded systems are not a memory luxurious systems. And that is what we need to respect, that particular memory availability, and because of which bare minimum services to be there in kernel, rest of the services to be operated from the user level with a proper interaction between user level and kernel level. Okay, that's what this particular statement says, that move as much as possible from kernel to user space. That means practically, if I see, the scheduler is a prima facie entity, time management is a prima facie entity. These two can be there into the kernel. Else otherwise, most of the part which is not related to scheduling and time management can be put into the user space. And then it can be used from the kernel space for exploration of the underlying architecture. It's as simple as that. Okay, fine. Then one of the example system that you can see that it's a match is an microkernel, where this Mac OS kernel, which is called Darwin kernel, is partly based on this particular match approach. As an example, we are discussing. So communication among the user module takes place primarily with the help of this message passing. Okay. Now, what exactly it means, let me just go a few slides further and let you explain it. So you can see here in this particular diagram of microkernel OS, you can see that this application program, file systems, or device driver, if being this used or being this program or being this written into user space, the interaction among these particular modules, can happens to be there with a message passing interfaces that routes through this particular kernel services. That's what, if you see this particular user mode and kernel mode, they are separated. And user mode makes use of the service of kernel mode through message passing interfaces in order to interact among the user mode applications or user mode services. This is what this particular line that we try and understand it. Okay, fine. Then what are the tangible benefit approach that you would have with this particular microkernel system structure? The very first benefit that you can think of is it just have an easier to extend the microkernel. So what your services, those you find as a custom made service for an embedded application. So that particular service can be used, can be extended into a piece of service into microkernel. Okay, and this is a facility that even we refer to be as a module facility, where we call as an LKM, called as a loadable kernel module, is happens to be there when you want to build up some service. You can have an interaction of that particular service with the kernel space only. Okay, so that is one of the tangible benefit that you'll get. The second benefit, as being it's a very bare minimum set of services, porting of those services for the underlying architecture, it also becomes easier for it. Else otherwise, every service needs the structural support from underlying architecture. You have to map, you have to marry the system functions, or you have to marry the functions which are being there into the kernel, which you wanted to make use for an underlying architecture. So system resources, the structural resources, and the application or the system functions, those are expected to be mapped, those are expected to be interfaced, and that exercise, as we already know, as a porting exercise. So fewer the services to be mapped onto the underlying hardware, it's always being an easier one and beneficial one. So from the porting perspective also, this microkernel porting to an underlying architecture happens to be an easier task of it. The next benefit that you can understand, it's more reliable. It's more reliable that in a sense that less code is running into the kernel mode. That means the fear of having some kind of malpractices or some kind of malfunctioning into the systems and corrupting the kernel from that process itself is very less probable. And that is what it said, that it happens to be a more reliable system to work on with. As per the security is concerned, as you need to register with the kernel, as you need to incorporate your services into the kernel with the help of LKM, which is loadable kernel module, into the runtime of an application, that expect to bring a lot of security even into this kind of system. This security is not as high as we would get from this layered or monolithic kind of kernel, but definitely some kind of security can be definitely availed with this kind of approach. Okay. Then the next part is how exactly we have benefited out of this in terms of the detriments. So detriments of this particular kernel, OS kernel, is it always has a performance overhead of user space to kernel space communication. And that is the only kind of drawback, or that is the only kind of detriment that one could see out of this particular microkernel structure. Okay. One more interesting thing that you should know is, in order to be able to make use of this microkernel architecture for your application programming, one has to be strong in the programming practices, because that's not so easy to program something with a kernel space. Okay. that we'll see subsequently when we are supposed to understand the embedded Linux. Specifically, we are going to write some drivers into the kernel, which will make them devices to operate seamlessly with the kernel services. So all this exercise are due in the next phase of this particular course when we discuss this embedded Linux. Okay, but at the moment, just understand as one of the determinants is this performance overhead is also being there. Overhead, why it is overhead? Because it really does not contribute to the functionality as such. When I'm saying that it's a message passing, interfaces are being used in order to have even within communication of the user space or user space to kernel space. It simply means that this could have been done in a seamless manner, but being there as a separated approach of the space, user and kernel space, you need to have some kind of integration. You need to have some kind of the dependency resolution, and that dependency resolution happens to be there with the help of this inter-process communication, which is said to be as an overhead for overhead of this particular user space to kernel space communication. Okay, so this is what in line with what we always discussed about operating system to be as an interface between hardware and the user mode. In the kernel mode, you can see that the bare minimum services that is being there is an memory management, CPU scheduling, inter-process communication. These are referred to be as an bare minimum services into the microkernel. Else otherwise the file system, device driver, application program, or some kind of uh, network protocol stack that is to be written and all that, that can be part of the user mode, right? So this user mode is separated from the kernel mode, and communication happens to be through this particular messages. Okay, so this is what we understand as an microkernel. The more insights of it we'll understand when we are going to see this MuCOS2 as a full-fledged operating system. Then let's move on to understanding a concept that we already discussed as a module concepts. Okay, so I'll quickly go through this particular module concept. These modules are also called as an LKM, as I said you. They're said to be as an loadable kernel modules. So many operating systems implement these loadable kernel modules. The basic approach is that it uses the object-oriented approach. That means whatever is being you required, you need to have that with running within kernel, even into the when the application is running. So in the running state of an application also, you can include some of the services into the kernel to get it done. Okay, so each core component is separate. As I say, it's going to be always an addition to that. So it's a topping of the services onto the kernel. So each talks to the others or known interfaces. That is obviously that has to be there with it. And each is loadable as needed within the kernel. So when I'm saying it's an as needed, it means that whenever you need it, you can have it. If you don't need it, don't occupy the space of, or don't expect to get that particular module occupy the space of kernel memory. That is what they can be loaded, they can be unloaded. And there are different shells, there are different commands which are being there, which we call to be as an insert and remove. If I say that insmod, there's a command, for example, this insmod will insert the module into the kernel space. As well, I have got the rmmod, remove module that can remove it. So once you are done with the job, whatever you wanted to get done from that particular function, so you can just get that particular module to be deregistered, decoupled from the kernel services, and you can just free that particular memory. So especially whenever we have got crunch of memory in embedded system, such kind of loadable kernel module approach is basically going to be a very interesting approach for design and development of embedded systems. Okay, so overall it is like similar to layers, but it has got more flexibility with it. Okay, so benefits, as we already discussed, it saves the kernel space, as well as on when required you can keep on adding those particular services or in the running state also. That is the major or prima facie benefit that you could have with the help of this particular module. Okay, so far what we have discussed is all about the basic functions, the types of operating system, the structuring of operating system, the benefits and drawback of every operating system, the outcomes, the tangible outcomes that we will get from this particular different structures. Okay, so everything that is being given into this very book called as an Galvin is one of the author of, which is the most favorite author of mine when I refer this particular operating system concepts. Okay, so I have specifically referred the 9th edition of this particular Galvin book. Okay. Then, as I said you that the reading material that I would pass on, but I'll encourage you to once again read it, the 10 things that you should know about the operating system from the internet sources. Okay. And then next time we are supposed to discuss the task management service of operating system with the task or process state transition diagram. We'll understand the control structure for the task management, that is the data structure in the memory, which is basically meant to control the various operations of this particular task management, like task creation, task deletion, uh, task resumption, task suspension. All this task management activity, we'll see that how this task control block would make contributions to the services. And we'll understand the scheduling mechanism and policy along with its differences. Okay. So I thank you for being into this particular discussion of operating system. Thank you.